As you know, electrons repel each other. Why then do atoms form chemical bonds? That question is not easy to answer in general, but with the toolset developed over the past weeks, it is possible to give you some understanding. Imagine a hydrogen atom, so a single proton and a single electron. The Hamiltonian of this system is to good approximation given by the electric potential created by the proton and the kinetic energy of the electron. It is not easy to diagonalize this operator, but it is possible, so let's just work with the results. The two states with the lowest energy are called 1s and 2s respectively. They are often represented by circles around the core, but please don't take this picture too seriously. It is only a crude schematic. The Hamiltonian of this system is rather boring because I purposefully restricted it to only two states, and those are already diagonalized. Now imagine a second hydrogen atom, keeping our first one company. Individually, it is described by exactly the same Hamiltonian, but once they come close, it is possible for our electron to hop into the unoccupied 2s orbital of the other atom. This is possible because the matrix element of the Hamiltonian between the two wave functions does not vanish. Again, with the knowledge of the form of the Hamiltonian and the wave functions, it is in principle possible to calculate the value of this matrix element, but for now let's just assume we had done that and call it t. This is often called the hopping amplitude. Because the Hamiltonian, as the operator corresponding to the energy, is required to be Hermitian, the transposed element has to be the complex conjugate of t. So now the Hamiltonian for one of the electrons looks like this. It is in principle also possible for the electron to get from the 2s orbital of the second atom to the 2s orbital of the first atom, but we'll ignore this interaction for now. Just as we ignored that the energies might change under the influence of a second proton entering the scene. Because the electron has, in this approximation, still no chance to get to the 2s shell of the first atom, we will ignore this orbital in what follows. Our two basis states are then H1 1s and H2 2s, and the Hamiltonian has a nice and simple form. Over time, due to interactions with the environment, the system will try to get to its ground state, the eigenstate with lowest energy. We are interested in the energy of that ground state, so let's do some algebra. The eigenvalues are given by the zeros of the characteristic polynomial, which is the determinant of our matrix minus lambda times the unit matrix. For a 2x2 matrix, this is easily calculated. Let's analyze this a bit. The coupling gives us two energies, which still have the same midpoint E1 plus E2 over 2. If t was 0, we would just get out E1 and E2 as expected, but if t is non-zero, then the peaks split farther apart. If the two energies are very far apart, then t has next to no effect, but if their difference is comparable to the absolute value of t, then it will have a noticeable effect. The most important takeaway here is that our new lowest energy is lower than it was before. This means that on this level of theory, having two hydrogen atoms close by is preferable to floating through space on your own. Of course, we have neglected many effects, most importantly the Coulomb interaction between the electrons, but if the energy gain due to this so-called hybridization is larger than the energy loss due to other effects, then a chemical bond is born. The eigenstates are now superpositions of our two basis states H1 1s and H2 2s. We say that the orbitals hybridized. It is possible to calculate how much of each character they possess, but it's a little bit more complicated. Try for yourself if you feel like it. Until then, enjoy life if you can, and don't be ashamed if you can't.